Hello everybody, this is Hitendra and this video is about exporting a part of the boom of a non-rotating telehandler from dynamic simulation environment to the stress analysis environment to see whether this part is able to withstand the load applied during the dynamic simulation. So this here is the assembly, which comprises of a chassis, the rear part of the boom, the sliding component of the boom, the forks, and there are three hydraulic cylinders, which one of which will be elevating the load, the other will be pushing out the sliding component from the boom out in the outward direction, and the third which will be keeping in level the blades of the forks during the elevation so that the the load on it doesn't fall off. So I will show you here. I'm sliding it out to show you from inside that we can see that there are rear pads fitted inside this rear component of the boom, and here on the top there are four sliding pads also on the sliding component of the boom, and in there is this hydraulic cylinder. So I will push it in there. Now I'll prepare this assembly for the entering the dynamic simulation environment here. Now we will enter the dynamic simulation environment. Okay, here we can see that excuse me. Now we can see that the chassis here is grounded, and the other components which will be in the motion, they are all under the mobile groups, and the joints which have been generated automatically depending upon the constraints and joints which have been applied to this assembly. All these standard joints are listed here. And then the gravity, as this assembly is quite heavy, so gravity is going to play a big role in the simulation during the analysis. So here we can see that these three hydraulic cylinders, I have defined the motion of these hydraulic cylinders during the simulation, as the duration of the simulation will be 7 seconds. So the position of, for example, the hydraulic cylinder which will be elevating the boom, we can see the properties here, that now presently it is at 50 millimeters. I will show you how. In the wireframe view, we can see this hydraulic cylinder, the position of this piston, the face of this piston is here, and the inner face of the hydraulic cylinder is here. I have redefined these faces manually so that I can calculate the real position of these two components, so that when I will enable the impose motion and using the position as a driving factor, I have defined that at 0 seconds, if it is 50 millimeters, then after 7 seconds it will be 900 millimeters. I have applied a spline curve so that initially it will lift slowly, then it will accelerate, and then it will slow down again to reach its final position, that is 900 millimeters. So the same way I have defined the initial and final positions of these hydraulic cylinders, the remaining two hydraulic cylinders. So I would like to say one thing, that we have to be very careful while we apply the constraints to the assembly, especially when we enter the dynamic simulation environment, so that this assembly is not over constrained. Otherwise we will not be able to get the desired results, as the forces and the reactions here will not be unique. So now I'm going to apply a trace to this assembly, so that during the simulation I want to see to which height, maximum height, this assembly, this machine is capable of lifting the load. So I will apply a trace here at this point, and as a reference I am keeping it as grounded. I want to see it in the output grapher also. So now I will click OK. Now we can see here that between the main part of the boom, the rear part of the boom, and the sliding boom, there is a prismatic joint here. So if we want, we can apply to this joint, we can enable the joint force here. For example, if I activate this, we can define here the dry friction coefficient here. Like there are wear pads present inside here, which will be sliding on the mild steel. So we can put the value of the dry coefficient of dry friction here, that is about 0.2, so that the forces calculated will be more real, and this assembly will behave more similar to the real world. Here I will keep it unchanged. Anyway, we can apply this, we can enable this joint for every joint force for every joint present here, as depending upon the material we are using, we can put the value of coefficient of friction here, so that this assembly is more similar to the real world assembly, the machine in the real world. So now I'm going to apply the loads also. I will apply a total load of 20,000 newtons to this assembly. To this blade, I'm going to apply 10,000 newtons. I'll flip the direction to define the direction of the load. It will be 10,000 newtons here, and another 10,000 newtons here. Okay. Now I'm going to make this assembly flexible, as I want to export this multi-body part of the rear component of the boom for the analysis in the stress analysis environment. So I'll select this part and click OK. Now I'm asked to define the load bearing faces here. So this point line joint here, the faces which will be bearing the load are this one. Then the pin in here is welded to these faces. Then the another pin for the main hydraulic cylinder is welded here. Then the shaft here, which is welded here to this part, these faces. Then I have to define the faces of the wear pads, which are fixed. So wear pad top, it is fixed on this face, and that on bottom. Then the right side, the wear pad, and the left side is here. Then there are the constraints I had applied, so it is asking me the constraints I had applied to this is point plane constraint I had applied to this face here. and the line plane on this one. So I have defined all the load bearing faces. I'll click OK. And now we are ready for the simulation. So this simulation will have a duration of 7 seconds. I'm going to run the simulation. Now we can see now slowly it has started to going up, as well as we will see in the right side view that the sliding boom is coming out slowly. And this black line, this is the trace I had applied to this assembly, because I want to know the capacity of the machine to lift the maximum height to which it can lift the load in the vertical direction. So it is going to take a few seconds. We can see it from the other side also. Okay. Now, when this simulation will be complete, when it will reach 7 seconds, after that we will be entering the output grapher, and this output grapher is a very important part of the dynamic simulation. Here we can get all the informations regarding all the joints excuse me, all the joints, to see the position, the force, acceleration, velocities of all these joints here. So here we can see that the blades here are, as this hydraulic cylinder is working, we can see that these blades are always in the position, in the same horizontal position as just as I defined it. Okay, the simulation is complete now. So now we will be entering the output grapher. It is still working. Just as it stops, I'll click on the output grapher. Okay, here we are. Now we can see here all these joints. I am interested in one joint in particular, rather two joints. The one when this cylindrical joint, when this piston is being pushed out of the hydraulic cylinder here, a lot of force is applied, and obviously that force is going to affect this body, this part also. So I will select this joint, cylindrical joint. I will look at the force, and here we can see the curve of this force, that in the beginning, when it is almost in the horizontal position, it has to apply a lot of force to lift this boom. So I will search for the maximum, and this is the position when it is applying a force of 198,926 newtons is being applied inside this hydraulic cylinder. So I will select another hydraulic cylinder which is pushing out the sliding component out, and I want to see the maximum force applied in that joint also. I will search for the maximum, and we can see here when this assembly, this boom is almost at its maximum outreach, the maximum force is acting here, because it has to work against the gravity. So I will select this time step also. Okay, now one more thing, the trace I had added, I want to know the maximum height to which this machine can lift the load, and it is in the vertical direction. That is, I will select EY for that, and I want to see the maximum value, and the maximum value is 5371 millimeters, and we can see that it has started from here, from -2 to 9. It is in minus because the point as a reference is a little bit above the face of this, above the position of the point I had selected. It was somewhere here, which is a little higher. So it started from negative and then it goes to the maximum value. So adding these together, we get approximately 5.6 meters of height. So this machine is capable of lifting this load to a maximum height of 5.6 meters. So now we have all the information we need to export these this part to the stress analysis environment. So this is the part I am going to export, and I have selected these two time steps where in two joints the force is maximum. So I will close this dynamic output grapher, and then I will finish the dynamic simulation environment. Now I will enter the stress analysis environment. Okay, I will create a study. Now I will select the motion load analysis, and we can see here detect and eliminate rigid body modes is automatically activated. Now you can see that there's just one part I have exported and there are two time steps. So I will start with the first 0.02 second time step. Okay. Now we can see these glyphs here, which are telling us the forces and reactions and the direction of those forces here, which are being applied, which are acting on this part. Okay, so now all the other parts and other components have gone in the background, only this part can be seen as solid. So I am going to hide the glyphs. Now, as the material has already been assigned, this is a multi-body part with all its reinforcing plates, and it is made up of mild steel. So there is no need to make any change here. The constraints have already been applied and the force also. So I am going directly to click automatic, detecting automatic contacts, as it is going to detect all these plates, the reinforcing plates here, and it is going to give them a bonding contact as they are welded to this main part. Okay, now we can see here that soon we can see the contacts here, and all the contacts automatically generated are bonded. So we can see like this plate, between this plate and this main part there is a bonded contact, and then similarly for all these reinforcing plates the type of contact has been applied as bonded. Now I will look at the mesh also. So I'm going to reduce the size of the mesh element by dividing it by 2. I will select create curved mesh elements. I'm not going to enter in depth in the argument of mesh because I just want to have an overall idea of how all the forces which are applying, how they are going to affect this part. So now I want to see the mesh view. Now it will run the computing of the mesh. Okay, so here is the mesh view of this part. There's fine mesh. Okay, now we can see here there are 19,545 nodes and 63,591 elements present here. So I'm going to hide the mesh view and we'll run the simulation. So here it starts. So now here we can see that the maximum force, the maximum von Mises stress here is 98.55 megapascals. I'm going to change the color bar settings so that we can see properly the areas which have high stress. So I will keep it at 40 megapascals. Now here we can see this red area. Here a lot of stress is induced, and I want to see the place where there is the maximum value of von Mises stress first. So this is here. At this point we can see the value of von Mises stress is 98.55 megapascals. We can probe to see in the other red areas the value of von Mises stress. Okay, it's 45.67. Now we will finish the probe. I will look for the displacement, maximum value of the displacement here. Still there is a possibility of improving, as the maximum value of von Mises stress is 98.55. We can see this area here. This has the maximum displacement, but its value is 0.1519, so it is quite negligible. No, I'm sorry. The maximum displacement is 0.3661 millimeters, so it is quite negligible. Similarly, we will have a look at the safety factor. Okay, so we can see here also all this blue is safe. This has a high safety factor in these regions, and the places which are green, yellow or red, they are we can say less safer. The value of safety factor is low there. I will see the place, the point where the value of safety factor is minimum. Obviously it will be minimum at that place where the value of von Mises stress is maximum. So it is here. It's 2.1, so it is we can say that this part will not fail under the loads which have been applied to this part. So now I will create another study so that we will say at the second position, the second time step we had selected, how it is going to behave at this time step, this part, how it is going to behave. I will click OK. We can see the glyphs again here, which are showing the direction of the load, the reaction forces which are acting on this part. Okay, now we can see that this is the second study. The first study was assigned this name, static analysis 1, and this is assigned static analysis 2. Okay, so I will activate the glyphs. We can see the direction of these forces and reactions over here. I will hide them again. Again, I will not assign the material. The constraints have already been defined. I will go to the automatic contacts so that it will detect the phases where the type of bonding, the type of contacts which have to be applied automatically to these reinforcing plates which are welded to this main part. Okay, now I will again go to the mesh settings. I will again divide the size of the mesh element by 2, and I will select create curved mesh elements. Now I will go directly on the simulation. I will run this simulation, run this study. Now we are almost there. It is computing the results, and now we can see here that the maximum value of one Mrs. stress here is 133.2 megapascals. So I'm going to see in the point where this stress is maximum. I'm going to change the color bar settings also, so that we can see the areas which have higher stress more clearly. So we can see the deformation here is exaggerated. I can reduce it to 0.5 times or even to its normal deformation also. Here we can see the deformation here at this point is maximum because the sliding component is at its maximum outreach, so a lot of stress is generated here, a lot of stress is induced here. We can see the point where the stress is maximum, it is here. We can run some probes also to see the values in these red zones, the value of the one Mrs. stress. Okay, it is 56.2 megapascals. So similarly we can see the displacement and safety factor also. So the displacement here is the deformation when these forces are acting on this part. It is for half a millimeter, so it is quite negligible, we can say. There's not too much deformation here. So now we can see the safety factor also. So the minimum safety factor will be at the place where the one Mrs. stress was maximum. So obviously it is going to be it is here at this point. It is 1.55. Although this part is going to resist the forces, it is not very safe, but there is a possibility of improving this model to improve this safety factor going beyond 3, so that we are sure that it is going to perform well. So this is it. If there are any suggestions or comments, you're all welcome. And I'm going to release a video in Italian language also about the simulation. And one more thing that I have then run a dynamic simulation of this telehandler where it comes forward, the stabilizers go down, and then it is going to lift this block, this marble block, to its maximum height. So thank you very much for watching. Thanks a lot.